Hi, my name is Lidice and today I'll be explaining how Bodhi plots are read and how to use them to understand real dynamic systems. So essentially, a Bodhi plot has two parts. It has a magnitude plot and a phase plot, and these show how a system responds to different frequencies, which is key in controlling systems and engineering. So a magnitude plot shows how the output amplitude compares to the input amplitude throughout the frequency. So the vertical axis is the magnitude in the unit of decibels, and then the horizontal axis is the frequency on a logarithmic scale. So the magnitude tells us how much a system amplifies or attitudes signals, and if oh my god, wait, this is so bad. Logarithmic logarithmic logar logarithmic logarithmic attenuates. Okay. Hello, my name is Lidice and today I'm going to be explaining Bodhi plots, how to read them, and how to use them to understand dynamic systems. So Bodhi plot consists of two plots. You have a magnitude plot and you have a phase plot, and these show how a system responds to different frequencies, and this is key in controlling systems and engineering. So first we have the magnitude plot. So this shows how the output amplitude compares to the input amplitude across frequency. So the vertical axis is the magnitude in the unit of decibels, and then the horizontal axis is the frequency with the unit or on a logarithmic scale. And then the magnitude tells us how much a system amplifies or attenuates signals. So if the magnitude is high, the system passes those frequencies well. And if it drops, the system filters or weakens those frequencies. So for a phase plot, it shows how the phase shift between the input and output. So essentially how much delay the system introduces at each frequency. So phase has the unit of degrees, and a negative phase means the output is lagging behind the input. So as frequency increases, systems usually introduce more phase lag, and this happens especially around like poles and zeros. Essentially continued what I explained. And then to essentially connect these ideas, you can imagine sending a sine wave into a system. So the sinusoidal input is represented by this equation, and then the system output is represented by this equation. So essentially, the output will still be a sine wave at the same frequency, but the amplitude may change and the wave might shift to the right, meaning it's going to lag behind. So magnitude tells us how much amplitude changes, and phase tells us how much delayed is coming in. Now, for converting from decibels and Bodhi plots, we, as mentioned, use the magnitude plot uses decibels as its unit. So decibels, they make large and small values easier to compare and turn multiplication into a simple addition. So the conversion formula is shown on the right here. It is the product of 20 and log 10 base with the gain in the argument. So for example, an example is if the gain is 2, then the magnitude is going to be about 6.02 decibels. And then, although not shown, if we had a gain of 0.5, you would have a magnitude of approximately -6 decibels. So this just makes using decibels makes it easier to analyze systems and design controllers in a more facilitated manner. So for the example, we can look at a real system, such as a DC motor. So the input is the voltage and the output is the rotational speed, which is in radians per second. And then can look at our graphs. So, well, before that, we also have the magnitude plot. So usually we have high gain at low frequencies, so the motor will follow the commands well, and then the gain drops when the frequencies are higher, so this motor can't really catch up and respond to these fast changes. And then for the phase plot, when you have a small phase at lower frequencies, there is less delay for when commands are slower. And then when you increase lag at higher frequencies, the motor reacts slower and it lags. So a motor behaves like a low-pass system, and it helps design stable controllers. So on the magnitude plot on the left, you can see that the high gain at low frequencies, meaning that the motor is following these slow commands very well. And then as the frequency increases, the magnitude drops, and this tells us that the motor cannot respond quickly to rapid input changes, so it behaves like a low-pass system. And then on the phase plot on the right, you see a little phase lag at these lower frequencies. So there's a delay for the slow signals, and then as the frequency is increasing, the phase is becoming more negative, meaning that the motor is responding slower and begins to lag behind the input. In a control system, this would help us with designing a controller, and it avoids instability and overshoot, especially when we're at these higher frequencies. And so in summary, the magnitude and phase plots in a Bode diagram tell us how a system behaves across frequencies and how much gain it provides and how much delay is being introduced. Understanding this helps us design stable and efficient control systems. Thank you.